Welcome, Calc students. Let's learn how to integrate. We've been down differentiation alley. We know how to differentiate all sorts of functions. But in calculus, we also need to know how to go backwards, how to integrate. Let's take a look at some examples right away and field some questions from some of my family members along the way. Stay tuned. So the first thing you want to realize is this. You know about the power rule with regard to differentiation. So in order to integrate, you got to use the power rule in reverse. And this is kind of the theme that you've got to remind yourself of again and again whenever you get a power function. The rule of the road here is to add 1 to the exponent, then divide by the new exponent. So when you're integrating a power function and you've got that exponent, what you need to do is add 1 to the exponent. That's the first step. You got to do these in this order. Add 1 to the exponent, then divide by the new exponent. Here's problem number 1. See if you can do it. We're looking at the integral of x squared dx. Well, the exponent is 2. Add 1 to the exponent. It's 3. So I'm going to have x cubed. Then divide by the new exponent. All right, so first thing, we're going to have x cubed. We arrived at that by adding 1 to the exponent. Now divide by the new exponent. My final answer is x cubed over 3 plus c. That c represents a constant. Question, Larry. Yeah, but why that plus c? Why do you need that plus c? That's a good question, Larry. So the plus c is necessary. Think about it 2 ways. Number 1, when you integrate, your answer is going to be a family of functions. You don't have any limits of integration here with problem number 1. So you're open to any function such that when you differentiate that function, you get the original integrand. You get x squared. So what you will get is an entire family of functions, not just one answer. So one thing we can think about is the answer that you're going to get to an indefinite integral is a family of functions. Any c value will work. Whether you put in 8, 6, 7, 5, 3, 0, or 9 for c, when I differentiate that, of course, when you differentiate a constant, you're going to get 0. So that part of it is no mystery. When you differentiate the constant, you'll get 0. When you differentiate x cubed over 3, you'll get the x squared that we begin with. So that's one way to think about this. The other way, just think about the fact that when you take the derivative of any constant, you get 0. So it makes sense to add the constant c. Otherwise, you're limiting yourself to just one answer when the truth is the answer to an indefinite integral is an infinite number of answers. Whatever number for the constant c you wish to put in. So you have to add that plus c and keep it open for business. You'll get used to that whenever you are writing the answer to an indefinite integral. You've got to add plus c. Here comes problem number 2. The integral of 4x cubed dx. Remember, I'm going to add 1 to the exponent, divide by the new exponent. Take a look. I add 1 to the exponent, get 4x to the 4th. Now divide by that new exponent. Don't forget to add plus c. The rest of the problem is a simple simplification. You got 4 over 4 there. 4 divided by 4 is 1. So the answer is going to be x to the 4th plus c. Question, Carrie. Yeah, can I check my answer by taking its derivative? Oh, so your question is, you're looking at x to the 4th plus c, and you want to take the derivative of that answer, see if you get back to the original. The answer is absolutely yes. It's a smart thing to do. It's almost like you have an answer document when you're doing these problems. So if you took the derivative of x to the 4th plus c, you'd get 4x cubed. Notice 4x cubed is the answer you start with, the integrand you begin with. When you take the derivative of x to the 4th plus c, you get 4x cubed plus the derivative of the constant 0. You get 4x cubed. Notice that is the same as the integrand we begin with. Always check your answers, a smart way to go. Barry, question. Yeah, can I factor out constants like I do when taking derivatives? You know how we factor out constants when we take derivatives? Can I do that with integration? That is a smart question, Barry. And yeah, the answer is yes. In fact, it's recommended. You will find that some of these integration problems get very difficult if you do not factor out that constant. So the recommend is always factor out that constant. Let me give you a look at what that looks like. Here's problem number 3. We're integrating 5x dx. The rewrite then, if I factor out the constant, is a 5 multiplier times the integral of x to the first dx. Now I'm just focusing on the integrand, which is that x to the first. I'm going to add 1 to the exponent, divide by the new exponent. The 5 is a multiplier. So I'm going to add 1 to the exponent, add 1 to 1, I get 2, divide by that new exponent. I'm now looking at 5 times quantity x squared over 2. Don't forget to add your constant. And you will find that final answers, like in the back of your textbook, are of this form: 5 halves x squared plus c. So remember that 5, just because you factor it out, it doesn't mean it goes away. It's x as a multiplier at the end of your problem when you write your final solution. Okay, so there's your third example. If you can factor out a constant, the recommend is not sometimes, always, always, always do it. Yes, question, Sherry. Yes, can I use this rule with negative exponents? Oh, that's a good question. So you've got a function with a negative exponent. Here's an example. Absolutely, you can use this rule with negative exponents. So our example here is the integral of 6x to the negative third dx. What's the story? You ought to be saying it to yourself at this point. Add 1 to the exponent, divide by the new exponent. Factor out that 6. There's 6 times the integral of x to the negative third dx. That's just a rewrite of the original problem. At this stage, when you add 1 to negative 3, you get negative 2. So I've got that factored out 6. X raised to the negative 2. Add 1 to the exponent, divide by that new exponent, divided by negative 2. Don't forget to add your plus c. Final answer, negative 3x to the negative second plus c. You see the 6 divided by negative 2, we arrive at that negative 3. X to the negative second plus c. So we are successfully integrating power functions of different varieties. Question, Gary. You have to. What if you have a function and it's raised to the power of negative 1? Don't you add one when you add 1 to that? Isn't we get 0? Won't you have a problem? Oh, that's a real good question, Gary. Let's take a look at what you're speaking about. What is the issue here? If the exponent is negative 1 and you have to add 1 to that exponent and then divide by the new exponent, let's see what's going to happen. Suppose you're integrating x to the negative first dx. You add 1 to the exponent, you get x to the 0. Divide by that new exponent, you're getting divided by 0. Alert, problem. Dividing by 0 results in an undefined answer. There's got to be a better way to roll. So here's the rule associated when you have an exponent equal to negative 1. Think of this original problem. It might occur to you as the integral of 1 over x. X to the negative first is equal to 1 over x. Think about this. When you integrate x to the negative first dx, I could rewrite that as the integral of 1 over x dx. I'm thinking in my mind's eye, what can I differentiate and get 1 over x? Exactly right. Natural log x. When you differentiate natural log x, you get 1 over x. So when you work backwards and you're integrating 1 over x, makes sense to you that you get the natural log of x plus c. Now it's required that you write not just the natural log x plus c, but the natural log of absolute value of x plus c. As the domain of any natural log function are all x's strictly greater than 0, you've got to take the absolute value of a negative number in order for this integral answer to hold water. So the rule of the road here is when you are integrating 1 over x, the answer is natural log absolute x plus c. A little different than just the power rule in reverse. When you get an exponent of -1, you got to have bells going off in your head. Question, Mary. Yes. What about cases when we have fraction exponents? Oh, your voice is cracking there a little bit, Mary. Let's do fraction exponents. Let's look at an example of fraction exponents. We can still use that power rule in reverse. So if I get integrate 3 root x dx, I can rewrite that as factor out the 3, integral of x to the 1/2 power dx, and I'm going to add 1 to the exponent, divide by the new exponent. Add 1 to the exponent. Well, when you add 1 to 1/2, that's the same as 1/2 plus 2 over 2. 2 over 2, of course, is just that 1 in disguise. And you get to the 3/2 power. All right, so things become a little, oh, you're dividing by fractions and so forth. So see if you can piece this puzzle together here with us. You add 1 to the exponent, you get 3/2. Then divide by the new exponent. We're actually dividing this time by 3/2. Remember, dividing by 3/2 is the same as multiplying by 2/3. Dividing by a fraction is the same as multiplying by its reciprocal. So when you piece this puzzle together, what you'll get is 3 integral x to the 1/2 power equals 3x to the 3/2 power all over 3/2, which is the same as 2/3 times that 3, x to the 3/2 power. You see that top-bottom relationship with the 3's cancel. Your final answer will be here 2x to the 3/2 power plus that constant c. All right, so that's a scenario when you have a fractional exponent, and you got to know how to divide by fractions, the same as multiplying by the reciprocal. Make sure you've got those lines of reasoning in order. Yeah, Harry, question. How do you integrate a constant? Oh, so you just have a constant and you want to integrate it, like this example, the integral of 5 dx. Not 5x, where you have an exponent on the x, where you can add 1 to the exponent, divide by the new exponent. We don't have that here. We have a simple constant 5. We want to integrate 5. Well, what do you differentiate to get 5? Of course, the answer is 5x. It doesn't surprise me here that the answer for how to integrate a constant is just tag that x to it and add c. So the integral of 5 dx is 5x plus c. How about trigonometry integration challenges? So we've worked nothing but power rule, but we also now know how to integrate 1 over x. We also now know how to integrate a constant. What about if I get sines and cosines? The rule of the road here is you use that diamond of trust for differentiation. Use the exact same diamond of trust for integration. But instead of working clockwise around that diamond, work counterclockwise. So here's the diamond of trust that everyone knows how to smack dab on their paper. Let's see if we can do an example here. The integral of 3 sine x dx. Factor out that 3 as a multiplier. Rewriting this as 3 sine x dx. And now let's look at our diamond of trust. I find sine on the diamond. I work counterclockwise to the next entry. I realize that the integral of sine is negative cosine. My answer then is -3 cosine x plus that constant c. So that gives you an idea of how to deal with power rule in reverse. Easy powers, negative powers, fractional powers. We also know how to deal with x to the negative first. We also know how to deal with integrating a constant and how to deal with integrating sine and cosine type challenges. So now that you know how to integrate, my question is, Have you figured out the name of the 8th person in this family? Let me tell you, Mr. Foster's mother had 8 children. I want to know the name of the 8th child. You've heard some other names in this video. See if you can figure it out. I'll take that answer when you return. This is Mr. Foster, Calculus Made Easy Integration Training. Hope you enjoyed. Over and out.